Hello everyone, this is K. Jain Sai from CSC B section and my roll number is 20951A0564. Today my topic is about reconfiguration of homomorphism. First of all, we discuss about homomorphism. What is homomorphism? In the mathematical field of graph theory, a graph homomorphism is a mapping between two graphs that respects their structure. This means we are mapping two different graphs with the same with a connection. More constrictly, it is a function between the vertices sets of two graphs that maps adjacent vertices to adjacent vertices. Homomorphism generalize various notations of graph coloring and allow the expression of an important class of constraint satisfaction problems, such as certain scheduling from or frequency assignment problems. The fact that homomorphism can be composed leads to rich algebraic structures, a preorder on graphs, a distributive lattice, and a category, one for undirected graphs and one for directed graphs. The computational complexity of finding a homomorphism between given graphs is prohibitive in general, but a lot is known about special cases that are solvable in polynomial time. Boundaries between tractable and intractable cases have been an active area of research. So now we will discuss about what is reconfiguration. Reconfiguration is a framework in which we study how discrete structures constrained in various ways and can be carefully transformed with small steps. This is often described by finding paths in a solution graphs whose vertices are all solutions to a combinatorial problem and whose edges define the steps between solutions one is allowed to make. A homomorphism from a graph G to a graph H is a mapping sigma from V of G to V of H such that edges are mapped to edges. That is, U V belongs to E of G implies sigma of U sigma of V belongs to E of H. We also use the name H coloring, especially when H is fixed in the context. Vertices of H are then called colors. Note that a KK coloring where H is the graph with all edges except loops is the same as a K coloring. We use graph for homomorphism as a tool to explore how different constraints influence the complexity of reconfiguration. As our aim is to give more general statements about reconfiguration, they should be seen as a special case of constraint satisfaction problems, which can express a range of problems including K coloring, generalized SAT, or independent set in weighted variance. However, graph homomorphism already display many features of general CSPs and arise naturally in various situations. For an excellent survey or Hill and Nestrel's book from on an in-depth look into the subject. This approach allowed the author to argue in that the only notion of sparseness that can be applied algorithmically to unparameterized reconfiguration problems in general is tree depth and that many such problems are PSPAC complete even in graph of bounded bandwidth with path width, tree width, etc. The reduction showed there explains why reconfiguration variants of easy combinational problems can be hard. This paper grew out of an attempt to find fundamental reasons for which reconfiguration variants of hard problems can be quite surprisingly easy. So that's about my topic, and thank you.